All right. So last week we talked about limits, and when we have a graph, a limit, no matter what the graph looks like, all right, maybe my graph looks like this. So here's the graph of f, all right? Yep. And then I want to know, hey, what's the limit as x approaches, let's call it 2, of my function, all right? A limit is defined as what's the y value we're getting close to. Yeah.
I don't have the note.
I passed them out to you. I passed them out to everybody. You should have the notes. I passed them out on Thursday. Yeah. You should have them. Check your folder. That big old mess. Yeah,
Pretty sure you were on your phone a while.
Yeah. Yeah, you've been a little addicted lately. You should look into that. All right. So a limit is simply the y value that we approach as we're moving in on the function from left and right. So as I'm moving in from the left, I'm approaching this value right here, which I'm going to call, I don't know, 1. And as I'm moving on my function from the right side, again, I'm approaching 1. And since they match, they both come to the same place, our limit is 1. Now, we also know that sometimes the limit does not exist. So maybe my function is coming down like this, and it lands right there. And maybe I have a function like this. There we go. So there's my crazy graph, my graph of f. And let's say this is -1. All right. So now when I say, hey, what's the limit as we approach -1 on this function f? So as we approach from the left side, yeah, this one, if we come just from the left side, what do we get? -1. But as we approach from the right side, what do we get? 2. Do they match? No. And this time they don't match, so the limit does not exist. So this is really important because when we approach from the left and the right, we want to come to the same value. So that's a limit. It's also important we understand that that actual defined point doesn't have to be there. Maybe f of 2 is actually like 3, and that's okay. The limit is just what do they get really, really, really close to, all right? Now, so that is limit. Today we're going to talk about continuity. And so continuity, if you look below here, continuity is informally when a function is continuous where it can be drawn without lifting a pencil. Were either of my functions here continuous? No. Neither one of them were continuous. For both of these, I had to pick up my pencil in order to draw it, all right? So these would be not continuous. Formally, a function is continuous where its limit and function value are the same. So if the limit from the left is equal to the limit from the right, so this is from the left side, from the right side, and if it matches the actual value, then that's the definition of being continuous. The left, the right, and the function value all have to match. So 3 things, really. Okay? So that is continuous. Oh, let's turn the page. All right, these are my notes from like 5 years ago. All right. So turn the page. So discontinuities. There are 4 types of discontinuities. One we already saw, so we can draw an example of that maybe. Maybe something like this. There's a hole, and then the function continues. All right. So this is an example of a hole. There's a hole in the function. It's got a little gap. All right. So that is a discontinuity. Vertical asymptotes are also functions where we have a vertical asymptote. Maybe my function looks like this. something like that. So that, of course, if we have a vertical asymptote, that would make something discontinuous. Jumps. We just drew a jump. I don't know, you can draw whatever you want, but maybe it looks something like this. There we go. There we go. Got a jump in the graph. Discontinuous, pretty easy. And then the one that is very different is oscillating. Oscillating discontinuities are rare, but I'll show you an example of one. The sine of 1 over x. The sine of 1 over x is crazy. Let me show you what that looks like. It's an oscillating, oh, I'm in totally the wrong mode there. All right, so oscillating discontinuity, 1 over x. All right, I'm going to show you, if I just do a zoom trig, this is what it looks like. All right, and maybe that's okay to you, but watch what happens when I zoom in really, really close. So I'm going to change the window, and I'm going to go from negative 0.25 to 0.25. And then I'm going to go from negative 1.2 to positive 1.2. And so there it is. And then, okay, this is an oscillating discontinuity. And this is just what the calculator can graph, all right? And what it did in the middle is it just oscillates between values so fast that we can't figure out a limit, all right, as we approach 0. And so this is sort of the example that it just goes like crazy here in the middle. But you can't figure out the limit as it approaches 0 just because it's oscillating so quickly. If you did 0.01 and then 0.011, you would get 2 different values, entirely different, okay? So it just is impossible. All right. Now, let's look at example 1 here. Maybe we know what they look like, but we can use our calculator to graph each. And would you say the functions are continuous on the interval? Can you trust your calculator? Can you trust your calculator? So, first of all, do you know what the shape of this graph is? It's a parabola. Oh, hey, you know what that looks like, right? Would you say that that parabola is continuous? Yeah, for sure. It's a parabola shifted up 1. All right, we know that that's a parabola. It has nothing crazy. It's a polynomial. These are always continuous. It is a polynomial, and a polynomial, anything like y equals x cubed plus 2x minus 7, any normal looking polynomial like y equals x minus 1. These are always going to be smooth curves, and they are always continuous. And if you know that, that is a great thing. Always continuous. So any polynomial is always continuous. So as long as none of the powers are wonky, they're all just regular positive integers, then you're good to go. This is a rational fractional function. What does it look like? It's a gang sign. It is a gang sign. It's this one, okay? So it has an asymptote. It does. Yeah, right here. Anytime you have a fraction, anytime we have that fraction, we get values that x is not allowed to equal. X is not allowed to equal 2. If you plug in a 2 there, what do you get? 0 in the denominator. Are we allowed to divide by 0? No. When the 0 is under, it's undefined. This has a vertical asymptote. Ought 2. All right. So is our function, if I were to graph it, 1 over x minus 2, I do a zoom standard, let's say. All right. Now, I only care about the interval from negative 3 to 3. I'm going to go ahead and change my window and just go from negative 3 to 3. Is this function continuous in my interval here? No. there's a big vertical asymptote right there in my interval, so it is not continuous on -3 to 3. And it's because we have a vertical asymptote at 2. All right? So you can use your calculator, but we really want to know just by looking at the function. This is why we've spent so much time graphing and thinking about things. Sine of x over x. Do you know what that looks like? A sine curve. It's probably something like a sine curve. Let's look. We don't know this one, maybe. Sine of x. WS. All right, and it says to go from negative pi to pi, so I'm going to go ahead and do that. I'm going to go from negative pi to pi on my calculator window. And I also doubt I need to go from negative 10 to positive 10, so I'm going to go negative 5 to 5. Oh, look at that. I really didn't need to even go to 1. All right. All right. Well, that's kind of interesting. So, do you think it's continuous? On that interval, you think it's continuous? Raise your hand if you think it's continuous on that interval. Looks like it, doesn't it?
Wait, can it be 0?
Can it be 0?
No.
Can x be 0?
Oh, no.
Oh, no. Yeah, it's a rational fractional function here. Again, denominators are not allowed to equal 0. So in this case, that x is not allowed to be 0. And you'll notice if I trace and enter 0, look at it. There's no y value. It's undefined. There is a hole there. Okay? And again, can you trust your calculator? This is the rule. You can't just look at the graph. So we also have to put together what we know about our function as well. It is...
What does that look like when it's zoomed out?
Further. It's just so it's the high is 1, and it just gets a little bit less every time. It goes closer and closer to 0 as it extends. Okay. All right. So is it continuous?
No.
No. This one has a hole. Not continuous. On negative pi to pi. All right. All right, let's look at this one. Again, I'm going to graph this one. I don't know what it looks, any ideas what it looks like?
X minus.
Just x minus to it. It looks like a line.
But there's a hole.
Okay, hey, very good. All right, this one we want to look from -3 to 3 for my window. So, oh, look, you can even see it. It does look just like a line, okay? Again, when we look at this rational fractional thing, we know right off the bat, x is not allowed to equal -2. That's in my interval here, within that. So we know it's not continuous right off the bat. But again, yeah, if you remember, this is something that we can factor. It double bubbles. And so this factors as x plus 2, x minus 2. And when you see that common factor that we can sort of reduce, that's what creates a hole at x equals -2. And so it's not a vertical asymptote, it's a hole. Okay. Which is kind of interesting. But again, not continuous on the interval. Is it continuous on the interval from 0 to 6? Yeah, it's continuous everywhere else. Okay. So this is just putting together a lot of stuff that we've talked about before, but turn the page. Use the graph of f. Here's my graph of f. I gave you the function here is 4 over x squared minus 9. What's the limit as x approaches 3? Does not exist. Yeah, we can see here that there's a vertical asymptote at +3 and -3. Where did that number come from? Where did those come from? Yeah, x squared minus 9. That factors as x plus 3 and x minus 3. And so those give you our vertical asymptotes at x equals -3 and +3. So those denominators are going to give you vertical asymptotes. Unless they cancel out, then they're whole. All right, so what do we say here? What's the limit?
DNA.
Does not exist, yes. The left side goes to -infinity. The right side goes to +infinity. And because they don't go in the same direction, that limit does not exist. What about the limit as we approach 0? How'd you get right here? So as we approach from the left, we're approaching this value. And as we approach from the right, we're approaching this. How do you figure out that value at 0? You plug in 0. It is an x value, so all we have to do is plug it in. So 4 over 0 squared minus 9 is -4/9. All right? There's nothing wonky we can plug in. All right, what is the limit as we approach -3 from the left-hand side? Yeah, so from the left of -3, I'm writing on my function, it's going up, 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 up. It's going up to where? +infinity. What is the function evaluated at 3? Yeah, why? Yeah, because you get 4 over 3 squared minus 9. So that'd be 4 over 0. And when the 0 is under, it's undefined. All right. We can also see that at 3 there's nothing there. It's an asymptote. It's undefined. Algebraically, when the 0 is under, it's undefined. Okay. Use interval notation to show where f is continuous. So on what intervals are we continuous? -infinity. So from the left all the way to -3. Union? -3 to +3. That takes that whole interval. And then union 3 to +infinity. So this is just all the sections where we see the graph. Parentheses don't include the value there, so we get infinitely close, but not including 3. All right, questions on those? All right. I'm like pages behind here. All right. Example 3. Use the graph of h to find the following. What is h evaluated at 1? I'm sorry, h evaluated at -1. Undefined. At -1, we have an open circle there. There's nothing there. It is literally undefined, as in it's not defined. All right. What's h at 1? 3, right here. Yeah, there's our solid dot. That's the one that's talking about. It is a y value of 3. The limit as x approaches -1. So we're approaching -1 right here. So from the left and from the right, they approach 1. They approach the same y value, even though it's not technically there. That's okay. For limits, that's totally fine. This is what is the limit as we approach +1 from the left side. From the left side, so coming in on the left side of 1, we're here, and that would be 3 for the output value there. And the limit as we approach 1 from the right side. So from the right side of 1, we're jumping on our function and coming in from the right side. That's just getting close to 1. Did they match? No, the limit from the left did not equal the limit from the right. What's the limit as we approach 1? Does not exist. Does not exist because they're different. Sad face. Okay. The limit from the left has to equal the limit from the right. Removable discontinuities. Well, we haven't really talked about which ones are removable, have we? Was it on that slide? Oh, it was on that side? Oh, I didn't read it, did I? I didn't read the second part of that out loud. Holes are called removable discontinuities because that's easy to plug. It is one infinitesimally small little hole, right? Easy to fill. We don't care about those. So holes are removable. We get to ignore them. Asymptotes and jumps are non-removable. Those things are too big to patch, all right? And so removable discontinuities would be at x equals -1. There's a hole there, all right? Non-removable discontinuities at x equals 1 is a jump discontinuity because we got a big jump there in our graph. Okay, questions on that? Okay. Moving right along. Good. All right, given piecewise functions, we're going to find the following. We want the limit as we approach 0 from the left. Which equation should I use if I'm approaching 0 from the left? The top one. This is x values littler than 0. This would be the left of 0. And so what do we have to do? Just plug it in. It's just an x value, so we're going to go ahead and just plug it into the top equation. 0 squared minus 2 is -2. And what's the limit as we approach 0 from the right? Which equation are we going to use if we want to go from the right side? The bottom equation. This is x is bigger than 0. This would be the right side of 0. And so once again, all I have to do is plug it in. So 0 plus 2, which is 2. Do they match?
No.
So what's the limit as we approach 0? Does not exist. All right. Again, these have to match. The limit from the left and the limit from the right must match in order for the limit from both sides to exist. What is f evaluated at 0? How do we figure that out? Yeah, that 0, we're only allowed to equal 0 on this top equation where x can equal 0. So we plug it into the top equation there, and we get -2. Is f continuous at 0? No. No, because the limit as x approaches 0 of f of x does not equal f of 0, the function evaluated at 0. The limit has to match the function value. Okay, G here. Here we want the limit as x approaches 2 on g of x. Ooh, what does this mean, the limit as we approach 2? What do we have to check? Both sides. We have to look at both limits. The limit as we approach 2 from the left of g of x, and we have to look at the limit as we approach 2 from the right side of g of x. All right, so I'm going to plug in my left equation here. I'm going to plug into the top. So that's 3 times 2 squared minus 2. What is that? 10. 4 times 3 is 12, minus 2 is 10. Good. And then from the right side, that is our bottom equation. So 2 times 2 plus 6, which is also 10. Okay, do they match? Yep. All right, so since they match, we know that the limit from both sides is 10. What's the limit as x approaches 0? Top. Why do we go to the top? Yeah, because that's where 0 is less than 2. All right, so that works there. So 3, plug in a 0, minus 0. What do we get? 0. Okay. Is g continuous at 2? Yes. Why? So do we know what g at 2 is? Yeah. How would we figure out g at 2? It's the first thing sort of. We just had to plug it into that first top equation. 3 times 2 squared minus 2 is 10. So yes, our limit as x approaches 2 of our g function is equal to g of 2. The limit must equal the function value. The limit must equal the function value. It's getting hot in here.
You good?
No, there's one more here.
No, like, you good.
It's getting hot in here. No. All right. Find the value of k that makes the function continuous. You'll notice there's some k's in here. So our job is to actually figure out what k must be. And in order to know that something is continuous, well, we've got a couple of things. The limit as x approaches, right here is where things are going to change. 2 from the left has to equal the limit as x approaches 2 from the right, which also has to be the same as f of 2. 3 sort of conditions. Really, it's 2, but because we have this little break in our curve, let's see, which equation is from the left here? Should it be the top equation or the bottom equation? Bottom equation. This is where x is littler than 2, so this is actually our left side equation. And this one is greater than 2, so this would be to the right side. So we want to be a little bit careful. So all I have to do then is say, hey, I want to know the limit as x approaches 2 from the left of our bottom equation here, kx minus 6. And it's got to equal the limit as x approaches 2 from the right. And the right, we're going to use our top equation, kx squared. Well, what do you do if you want to figure out a limit? We're plugging in an x value is essentially all we're doing. So this is my x value. We're going to just plug in our x value. So k times 2 minus 6 equals k times 2 squared. So we're just plugging in our x value, and I'm going to clean it up a little bit, so I get 2k minus 6 equals 4k. Good. We can subtract 2k from both sides. We get 2k equals negative 6, which means k equals negative 3. Oops. Well, there's one thing I am going to say. If this question were ever on, did we ever verify f of 2? We did not. Okay. So if this were on an AP question, you would need to verify them to show that they're all the same. I'm going to plug in my k value, so negative 3x squared. So I'm just plugging in the number we found, negative 3x minus 6 when x is less than 2. And I want to go ahead and just find f of 2 and just make sure we can also plug in the limits, but they should all match. F of 2, if I plug in my 2 here, 2 squared is 4 times 3 is negative 12. I think the best practice would be to check my limit from the left, but this is pretty easy to plug in. From the left, it would be negative 3 times 2 minus 6. That is also negative 12. And the limit from the right. So using my right side equation, which is the top equation, negative 3 times 2 squared, 4 times minus 3 is also negative 12. So yes, it is continuous. F is continuous when k equals negative 3. That would be full credit on the AP test. But they're never going to ask this question. It might be a multiple choice question, though. As in, you'd need to solve for k. So that does come up. No. Do I encourage you to show your work?
Yeah.
Of course. All right.